Welcome to week 10, lecture 1. We are talking about gravitation. This is from chapter 14, 14-1, 2, and 4. So Newton's law of universal gravitation, gravitation near the Earth's surface, and then we're going to do 3 sample problems. Newton's law of universal gravitation says every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The direction of the force is along the line joining the particles. So let's see what this looks like. We have 2 masses here, big M and little m, and they're separated by a distance r. Apologies for the pixelated image. Each mass is experiencing a force due to the gravity of the other mass. The force is given by this equation here. Force equals Gmm over r. G big M little m over r squared, excuse me. And where those m's are the masses, r is the distance between them, and g is this here, the gravitational constant, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. You don't have to memorize that. You just need to have access to it somewhere. Although if you are going to get your degree in astronomy, you will memorize it. So here we have the 2 masses. Instead, these ones are labeled M1 and M2. And they're each experiencing an attractive force from the gravity of the other one. So mass 1 experiences force 1, 2, which is force on 1 by 2. And then mass 2, force 2, 1, which is force on mass 2 by mass 1. And these are action-reaction pairs of forces. So they're equal in magnitude and opposite in direction. We can generate equations for both forces. In doing this, we also introduce the unit vector representing the direction from one mass to the other. It is a unit vector just like I, J, and K hat, where it has no units or dimensions. It has a value of 1, and it just indicates the direction. So for the force on mass 1 by mass 2, we have this here, negative G M1 times M2 divided by R12 squared times R hat 1, 2. And the negative sign here just indicates that R hat 1, 2 and S1, 2 are in opposite directions. We can also, the equation relationship for r hat, maybe even just like a definition of it, given by the vector r12 divided by the magnitude r12, which really this results in a unit vector pointing in the direction of the vector. Yeah. And we can get the same relationship for the force on mass 2 from mass 1. It's still negative G M2 M1 over R21 squared times R21 hat. But it just acts in the opposite directions of force 1, 2 and the unit vector R12. So force 2, 1 points from 2 to 1. Hey, that's a helpful tip. And force 1, 2 points from mass 1 to mass 2, where R12 points the opposite direction, and same with R21. So when talking about gravitation at the scale of the solar system, we have to take into account that all bodies in the system have gravitational attraction to each other. So when thinking about the Earth, there is a gravitational force from the sun but also one from the moon, for example. In order to find the total gravitational force on the Earth, we need to sum those. So this process, along with being vector addition, is also known as the principle of superposition. We find the gravitational force between the Earth and the moon as though the sun isn't there. And then we find the force between the Earth and the sun as if the moon isn't there. And then we combine those forces to find the total force acting via vector addition. And this concept of superposition is something that's definitely going to come up in electricity and magnetism. Now gravity or gravitation near the Earth's surface, we can input the mass of the Earth here into this equation. And we also know something else. We have the weight force near the surface of the Earth, which is given by the mass times the local acceleration due to gravity. If we set these forces equal to each other, and this is the same mass because it's just whatever object we're looking at, then that mass cancels out and we end up with an equation for the local acceleration due to gravity, which is g, again, the gravitational constant, times the mass of the Earth, times the radius, or divided by the radius squared. So on the surface of the Earth, the radius squared is just the radius of the Earth squared, but this is also applicable to different distances from the surface. So if we're on the surface of the Earth, we can plug in the mass of the Earth, the radius of the Earth, and we get a familiar value for little g. We get 9.8 meters per second squared. This is where our value for the gravitational, local gravitational acceleration comes from. It comes from Newton's law for universal gravitation. Newton's law for universal gravitation. This table shows values for g naught, or little g, at different altitudes above the surface of the Earth. So on the surface, there's 9.83. That actually depends on where you are on the surface of the Earth, because the Earth is not doesn't have uniform density. So there are parts where gravity is stronger. And an airplane 10 kilometers above the surface, it's 9.80. At the top of the atmosphere at 100 kilometers above the surface is 9.53. And then we can go all the way to the moon, and the force, the value at the distance of the moon's orbit is 0.0027 meters per second squared. And now we're going to do our sample problems. I'll read this first one. Calculate the magnitude of the gravitational force exerted on a cantaloupe of mass 1 kilogram on the surface of the Earth. Sorry, I think that is also giving us the radius potentially. We'll get back to that part. But due to the Earth, the moon, and the sun. So let's do that. Okay, I wrote the relevant variables for us ahead of time. So remember, our equation is g m over r squared. So for A, we want to know the force from the surface of the Earth. And for that, I'm just going to use the weight force because it just saves us some time, because really we already know what that part is. It's little g. And then the mass is there. So we don't have to reinvent the wheel every time. So just 1 kilogram times 9.8 meters per second squared gives us 9.8 newtons for the force on the surface of the Earth. And then we want the force by the moon. And we have the radius here in this one is the distance from the Earth to the moon. And then I have the mass of the moon. So GMM, that's a subscript, and then little m over Rn squared. See, I'll just put it down here. So G is again 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then mass of the moon is 7.35 times 10 to the 22 kilograms. Our cantaloupe is 1 kilogram. And then the distance is 3.844 times 10 to the 8 meters, and that is squared. And this gives us a force of 3.32 times 10 to the negative 5 Newton. So not a huge force from the moon. I'll label that one Earth. And then finally, from the sun, so force, so 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared for G. And then we have the mass of the sun, which is 1.989 times 10 to the 30 kilograms. And 1 kilogram for a cantaloupe. And then the distance between the Earth and the sun is 1.495 times 10 to the 11 meters, and that is squared. So this gives us 5.93 times 10 to the negative 3 newtons from the sun. So obviously the force from the Earth is the biggest because it's on the Earth's surface. But it's interesting to see that even though the sun's a lot farther away, because it's a lot more massive, it acts with a stronger force than the moon. Okay, let's go to the next question. So for this one, we have an astronaut with a mass of 105 kilograms drifting through the asteroid belt on a mining expedition. At a particular instant, he is located near 2 asteroids of mass M1, 346 kilograms, R1, 215 meters. That's the distance between them. And then mass 2 is 184 kilograms. Distance to that is 142 meters. And the lines connecting the asteroid to the 2 asteroids to the astronaut are at an angle of 120 degrees. So we want to know what the magnitude and the direction of the gravitational force on the astronaut is due to these 2 asteroids. And we're gonna assume that they can all be treated as particles so that we don't have to worry about like the astronaut's arms in the motion. So let's start by just writing our knowns. Mass astronaut is 105 kilograms. Mass of asteroid 1 is 346 kilograms. Distance to asteroid 1, 215 meters. And then mass asteroid 2, 184 kilograms. Distance to asteroid 2 is 142 meters. Okay, I think that's what we need for right now. I guess I'll also just write this equation because we are learning it, so it's good to have a reminder. So this has to do with the concept of superposition that I talked about, where we find the force on the astronaut from mass 1 as if mass 2 isn't there. And then we find the force on the astronaut from mass 2 as if mass 1 isn't there. And then we do vector addition. So that's what we're going to do. So we are going to start with let's see. The astronaut, and we'll just start with mass 1. G is again 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then we'll say the mass of the asteroid first, 346 kilograms. And then the mass of the astronaut, 105 kilograms. And then the distance between them squared, 215 meters squared. And so this gives us force on the astronaut from asteroid 1 equals 5.24 times 10 to the negative 11 newtons in the I hat direction, because that is this one here. Then we'll do maybe I'll give myself a little more room actually. For the force on the astronaut from mass 2, again, 6.67 times 10 to the negative 11. And just this is why, if you're going to be an astronomer, you will have it memorized, because you're going to use it a lot. Anyway, 184 kilograms for the mass of asteroid 2 times 105 kilograms for the astronaut, and the distance between them is 142 meters, and that is squared. So we end up with force on the astronaut from asteroid 2 is 6.39 times 10 to the negative 11 newtons. And we will just give that the R hat A2 because you can see that this direction, but it's not really defined at the moment, but we will have to define it because we want the net force, not just the force from each of them. So let's look at a couple of things. First, I'm going to just draw our forces out on this diagram. So we have this one is FA1, and then FA2 is this way, FA2. And then we were told that that angle is 120 degrees, but we really want this angle, and that is going to be 90 because this whole quadrant here is 90. Or sorry, 120 minus 90. So theta equals 120 minus 90, which is 30 degrees. Okay, so then we want to look at the force on the astronaut, so the total force. And I'm going to write this in unit vector notation for now. So it's just going to be the force from asteroid 1 minus the force from asteroid 2 in the x direction. And that's minus just because the force from asteroid 2 in the x direction is just in the negative x direction. And this is I hat, and then J hat is gonna just be the y component of the force from asteroid 2. And one thing, well, first I'll just write over here that the x component of 2 is sine of theta, so FA2 sine theta. The y component is cosine of theta, FA2 cosine theta. So that's what we'll plug in there. And then one more thing that I want to note is that this value is actually 63.9 piconewton. Piconewtons. And that is, what is that? 10 to the negative 9 is a pico. So it's just making it easier. You don't have to write it that way, but that way I don't have to write times 10 to the negative 11 each time. So piconewton. And that's what we're going to plug in here. So the force from asteroid 1, 52.4 piconewtons minus force from asteroid 2, 63.9 piconewtons times sine of 30 degrees. And that's I hat, and then J hat is just 63.9 piconewtons times cosine of 30 degrees J hat. So this gives us 20.45 piconewtons in I hat plus 55.34 piconewtons in J hat. But we want now from that to get the actual value of the overall vector. So that's just where we do the square root of them squared and added together. So square root of f a x squared plus f a y squared. Square root of 20.45 piconewtons squared plus 55.34 piconewtons squared. And this gives us, for the net force on the astronaut, 59 piconewtons, which is again just 5.9 times 10 to the negative 11 newtons. Finally, we need to know what angle it is. So we know it's like somewhere in that part of the xy coordinate axis, but we want an angle for it. So let's say we want this angle phi from the positive x-axis. That's a good one to take from. So that tells us, just change color. Tangent of phi is opposite over adjacent, so the y component over the x component. And the angle phi is tangent inverse of 55.34 piconewtons divided by 20.45 piconewtons. And that is an angle of 69.7 degrees. So briefly to go over this, we found the force from asteroid 1, ignoring asteroid 2, and then we found the force from asteroid 2, ignoring asteroid 1. We figured out the x and y components of both of those technically, but the force from one was just in the x direction, the other one had other components. And we solved for the net force using unit vector notation. But then we had to get the final value by doing the square root of them squared, and finally we got the angle. We can have one more short example. This one's much shorter than that one. So we have a neutron star with mass m equal to the mass of the sun, which is given, they gave it as 1.99. I had 1.989. Times 10 to the 30 kilograms, and a radius of 12 kilometers. What is the free fall acceleration at its surface? And we're ignoring rotational effects, and this is especially important for neutron stars because they spin really fast. So remember, the equation G naught is a gravitational constant, mass of the object, and then the radius of the object squared. So 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times 1.99 times 10 to the 30 kilograms, all divided by 12 times 10 to the 3, so that I get it in meters, squared. And that gives us a ridiculous local gravitational acceleration, 9.22 times 10 to the 11 meters per second squared. So local acceleration due to gravity on the surface of a neutron star, which you shouldn't be on anyway because lots of other reasons, but that gravity is huge in comparison to on Earth, it's just 9.8. So it's pretty much 10 to the 11 times stronger. So that's all for this lecture. Have a great day.